Hey guys, so today's topic is about the binomial distribution formula. Um, so I'm going to explain kind of the requirements to use this formula as well as, the step-by-step process. So just before I dive into this problem, the binomial distribution formula, it's really just a formula that consists of three parts. And the parts themselves are really not difficult. You've done them ever since probably middle school. But so you use the binomial distribution formula when there's certain requirements. The first requirement is, and I really don't want to. The first requirement is that the probability between every single trial remains constant. So, like flipping a coin, 20 times. The number of trials is finite, so that has to be 1. The trials themselves are independent of each other, so the probability of success or failure will always remain constant. So, if I flip a coin, the probability of me getting a heads, which, say if I want to get heads, then, the probability of me flipping a heads would be 50%, about 50%. And that's every single time you flip that coin. No matter what, the probability that you get you land on a heads is never going to change, no matter how many times you flip that coin. So probability of success remains constant. Also, the number of trials is finite. So that means there you can count how many trials you have. It's not like an infinite amount of trials where it just never ends. What else? So I said that, and so the main thing. Oh, also the most important one. There's always only 2 outcomes for every single trial. So heads or tails, or a person living, dying. So living would be a success, and then dying would be a failure. So in clinical trials, obviously, success is the person living, and then dying is the person failing. So with binomial experiments, every single trial, no matter how many times you repeat it, it will always have only 2 possible outcomes: success and failure. There's no middle ground. And that's actually, where the word binomial comes from, the prefix bi. So 2 possible outcomes, probability remains constant, and the trials are independent. Okay, so those are the main ingredients for when to use this formula. And I'm going to go ahead and explain this solved problem, and then we're going to solve a couple problems together. And I'm going to go ahead and link some really great online free calculators that are websites, and they're great. So even if you don't have a graphing calculator at home, if you have internet connection, which, if you're watching this, you do, then you can easily calculate the probabilities, which don't do by hand, ever. So let's talk about this example. So 81% of companies use networking to recruit new employees. The probability that in a survey of 14 total companies, exactly half of them use this recruiting software is what's the chance of exactly half of them using this new recruiting software? So 14 total companies, exactly half would be 7. So N would be, and I have this here, is your little key. This is the formula that we're going to use today. And it looks, intimidating, but it's not. N is just the total number of trials, or the total number of the total sample size. X is your number of desired success. P would be your probability of success, which again remains constant no matter what. Q is the probability of failure. So if you know what P is, you can easily find Q because they're complements of each other. So 1 minus P will give you Q. And then here is mu. That's the Greek letter mu. It's like this long line with a U attached to it. And then it represents the mean, which is just n times p, n times p, n times p. And then the variance, which is n times p times q. And then, so that's sigma squared, so Greek letter sigma. And then that's just sigma. Sigma, which stands for the standard deviation, which is the square root of the variance, square root of n times p times q. And so all this seems like a lot at first, but I think you guys are going to get it. So this is the formula in question. And these are all I've already labeled, listed, and decided what variables are, assigned to what numbers. So n is your total number of, the total sample size, which is 14. X is the number of successes, the number of desired successes. And they said they want exactly half, so that would be 7. P is your probability of success. So they want to know how many actually use this software, so that would be 0.81. And then Q, which I got from subtracting 1 from P. So 1 minus 0.81 gives me 0.19. So that's all of our variables, assigned values. And this is the relevant formula, and we're going to go ahead and plug in the numbers. So this is just the probability that we care about. This is our final answer. And so if you don't know what combination is, go ahead and watch one of my other videos. I talk about combinations a lot. But for now, let's just move it along. So 14 combination 7. 14 combination 7. This is the probability of success. 0.81. 0.81 is raised to the x power. So 0.81 raised to the 7th power. 0.19. So Q is raised to n minus x. N minus x. 14 minus 7. So right here, I'm just plugging in the numbers. Here, I'm going to simplify just a little bit. I will not do this by hand. There's a calculator for that. You don't do this by hand. You don't do this by hand. You don't do anything by hand. So here, I just subtracted to get the final exponent. Notice the fact that I placed the exponent inside the parentheses. You don't want to give the calculator any room for error. Really, it would be human error because you inputted it incorrectly. But you really have to understand that the 7 is attached to the 0.81. If you accidentally place it here on the outside of the parentheses, it might go ahead and just take this whole and raise it to the 7th, as opposed to just this. Only this needs to be raised to the 7th, not this. So I personally like to put the exponent on the inside. And then 0.19 raised to the 7th. So after you get to this point, it's very smooth sailing. You can easily find a calculator online, and I'm going to link a couple great ones down below in the bio. I'm going to repeat myself. Do not do this by hand. Nobody does this by hand. And so your final answer in decimal form, before we convert it to a percent, because that's what people care about is percentages. It really puts things in perspective, I feel like. 0.0702. When you convert to a percentage, you move it 2 spaces to the right, and you get, as your final answer, 0.702%. So there's actually a less than 1% chance that exactly 7 companies out of 14 will be using this specific recruiting software. And that's really it. The hardest part, really, I think, is determining, honestly, is determining the number of desired successes, because sometimes they do get a little wordy, but for the most part, word problems when it comes to the binomial distribution formula, they're pretty straightforward. So go ahead and you can pause right now, and you can pause to see, to like soak in the whole problem. But we're gonna go ahead and do a problem together now. So, okay. So this is, we're going to solve this together. So example 2, a die is rolled 3 times. The variable x is defined as the number of times the die lands on a 6 in 3 tosses. So I toss it once, second, 3 times. How many times do I land on a 6? And so n is the number of trials, which is 3. So 3 trials. X. So let's talk about, let's leave X for last. Probability of success. So what are the chances that I roll a die and it lands on a 6? 1/6. Okay, and that converts to 0. Let me erase it. 0.1667. And then Q would be 1 minus P. So 1 minus P, which is 1 minus 0.16667. Okay, so 5 divided by 6, 0.8. H, 3, just repeating 3. Okay, so X is honestly the most complicated part. So X is defined as the number of times the die lands on a 6. So if I roll it 3 times, there is a possibility that I never get a 6. So in that case, X would be 0. So there was no success in that situation. There is a chance that I only get 1 6 out of 3 rolls. So that's 1. There's a chance I get 2 6s, right? It's not a high chance, but it is a chance. So 2 successes. And then there's a chance that I get a 6 every single roll. So that's 3 successes. Okay, so there's 4 different scenarios of you roll a die 3 times and how many possible times out of those 3 rolls you get a 6. So now let's go ahead and rewrite the formula and then plug in the assigned values. So this is your formula right here. So this is just the probability that we're looking for. NCX P raised to the X, Q raised to the difference of N and X. So now I'm going to rewrite the formula with the assigned values. Except there's 4 X values. So I'm going to have actually 4 parts to this final answer, and I'll explain. So here is how I want to do it. This is how I want to do it. So the probability that X equals 0 plus the probability that X equals 1 plus the probability that X equals 2 plus the probability that X equals 3. So there's a shorthand for this. It's the greater than less than. So I'm going to go ahead and make my life easy. This whole thing, repeated 4 times is already like way too much work for you to do by hand, like we did in example 1. So I'm going to make my life even easier by shorthanding, and then there's even a specific function in every single binomial distribution calculator to where you can input it like this. So I can rewrite this entire line as the probability of x being less than or equal to 3. So this is equal to this. So 0 is satisfied, 1 is satisfied, 2 is satisfied, and 3 is satisfied. 4 is not satisfied, and that works perfectly for us because we don't care about 4. So this is the same thing as this, okay? So what we're going to do is I'm just going to briefly show you the setup for this one and this one, because it gets repetitive. At a certain point, you're going to be like, okay, we get it. So let's do the probabilities, just the setup, because after you set it up, you just give it straight to the calculator. So the probability of x equals 0, so let's set it up with this formula. N, which is 3, let's do it in block. Erase. So 3, following this formula, combination, x here is 0, okay? The probability of success, which is p, you could do the fraction or the decimal, doesn't really matter. The fraction is honestly more accurate, so I'll just do the fraction. So 1 out of 6, oopsie. 1 out of, you know what, I'll do the decimal because that way it's easier to see the exponent. 0.1667, and I'm going to raise that to the x power. So in this case, x is 0. Okay, and now my final portion, the third part, is q, which is 0.833. Raised to n minus x. N is 3. Minus x here is 0. Okay, so your final is going to look like this. 0.1667 raised to the 0. 0.833 raised to the third. Okay, and you know that anything raised to the 0 is 1. So I'm going to make my life even easier. 3, choose 0. And I'm just going to eliminate that. Put that right here. Drop this down. 0.833 raised to the third. And you can do this by hand if you want to, or you can just give it all to the calculator. You can even put this straight in the calculator, but I just feel like this would be easier. And so now, your final answer is 0.578. For not your actual final answer, your final answer for this part, because keep in mind you still have this, and this left. So this is just the setup for the probability when x equals 0. And I'm going to do one more. I'm just going to do the probability of x equals 1. But this process is repeated 2 more times with different x values. And the calculator that I'm going to link does this all in one single step. But I really want to explain like the algebra that goes into this. So let's do x equals 1 now. Okay, so notice I left a lot because it doesn't change. The only thing that kind of changes is some of the variables. So n, which is 3, choose 1. N choose 1. This is the p value raised to the x value, so raised to the first power. This is the q value raised to the difference between n and x, so 3 minus 1. Okay, so I'm going to simplify a little bit. 3, choose 1. Anything raised to the first power is just itself. So 0.1667, close the parentheses. And now I'm going to simplify the exponent a little bit, 0.833 to the second power. At this point, you can just put it straight in the calculator and it will give you the value that you care about, which is 0.348.